Hey everybody, this is Mr. Piercy, and what we're going to be looking at in this video are going to be some properties about tangent lines and how they relate to circles. Now, as a little bit of background information, uh, circles are probably the second most significant shape in math behind specifically right triangles, but triangles in general. There's a lot of things that you probably know about circles already. So if you're looking at the vocabulary terms here and the pictures as they relate to the circle, the diagram that I'm providing here, you probably know some of them already. If I gave you a picture and I asked you to identify what's the radius, what's the diameter, maybe what the circumference is, maybe what area is, there's probably things that you know already. Um, Here we're going to be looking specifically at first identifying just some parts of circles, and that's what all of these segments are. But this lesson is going to focus on properties of tangent lines first, and we'll revisit the idea of chords and secants and things to do with angles in future lessons in this unit. So if you need to, go ahead and pause the video and make sure you get the vocabulary down. When you're ready, go ahead and hit play, but we will move on for the time being. Now, the first thing that we're looking at here, because we're talking about, we have these segments inside of the circles, tangents, secants, chords, etc. Can you identify what they are? So segment BC, what we're looking at here is just this bit, and looking at that, you can probably say, well, it goes from the center of the circle to the edge, so it is a radius. Moving to segment EA, well, EA is this line. It goes through the circle at 2 points, so that is the definition of a secant line. Now, secants don't have to be lines. They can be rays and line segments also, and the last one here that we'll kind of take a look at, ray DE. So I'm starting here at D and I'm going that way through E, and I'm only touching the circle at one point right there at B, so that makes it a tangent ray. So this is just, again, to make sure that if you see something in a circle, one of these segments, that you can correctly identify them, or if I ask you to create one, you know what it should look like to make one. Here, these are going to be fairly straightforward. I'm not going to spend a lot of time on this. There is going to be a little bit of stuff on an assignment about it, but that's about the limit of it. We're looking at a circle on a graph. Can we identify the radius and the diameter of them? Well, the radius of A would be 2 units, so its diameter would be 4 units. The radius of circle B is 1, 2, 3, 4 units, so its diameter would be 8. And that's really kind of all we're looking at here for finding the radius and the diameter of a circle. Again, that's one of those things that probably everybody could do already. All right, go ahead and pause the video at this point and answer these 2 questions. And when you're done, hit play and come back and see how your work looks with mine. Okay, so in example 1, or question 1, we're going to go back to example 1 and tell what segment AB, what is it best described as and why. Here, if you go back and you look at it, that will be a diameter because it is a chord that goes through the center of the circle. And can you find the radius and the diameter of these? And I think I have a typo on here somewhere. There we go. Somewhere is there we go. So part A is asking what's the radius of C, and that is 3. But part B was asking what's the diameter of D, and I wrote the radius again. So here, that should be a 2 for the diameter. Now here, now we're getting into specifically stuff we're going to be doing with tangents, which is what most of this lesson is about. Can you draw circles that have common tangents? Well, if a circle has a common tangent, the line segment array must only intersect each circle in only one place. It can't go through the circles at all. So here I have two circles that are tangent to each other because they're only intersecting each other, or they're not intersecting, but they're touching each other at one point here. And so you can see that in this case I can create three common tangents to the circle. In the next one I can get two, and then the last one I can only get one because just like in A, the circles in C are tangent to each other, but the smaller circle is in the interior of the larger circle, so they only have one common point of tangency. Here we're going to just kind of follow up on that idea, draw the common tangents in the circles that you see here. So go ahead and hit pause and do so. When you have your tangent lines, go ahead and hit play again and see what yours look with mine. All right. So number 3, there's somewhere I have my answer here. Somewhere I have my answer. Oh, I must have moved it. There we go. There are no common tangents here. For this one, there will be 4 common tangents. The most common answer on that one would be 2 that I see students give me in class, where they kind of give me, they'll kind of give me this one here and this one here, but they don't quite see the 2 that kind of go through in between the 2 circles. All right, so now we're getting ready for our really good stuff here, and there's going to be there is a demonstration video that shows you this property here. What we're looking at is if I have a line, whether it's a line segment, array, if it's tangent to the circle, it will be perpendicular to the circle or to the radius at the same point. So here you can kind of see in the picture, we have radius OP, but I also have line M tangent to the circle at the same point, P. Therefore, the tangent line and the radius of the circle are perpendicular to each other at that point. And so if they are perpendicular to each other, what we can do is we can create right triangles. And what you can kind of see down here in example 4 is we have a segment RS and we have this other segment TS and this segment from the center RT, and we want to know, does it form a right triangle? Because if it does, then segment TS will be tangent to the circle. So that's how we're going to use our Pythagorean theorem again here. And so if it's a right triangle, we will use the Pythagorean theorem to show that it works. And in this case, 26 squared will equal the other two sides, 24 and 10 squared. And so in this case, we do have a right triangle. Therefore, I would say, yes, segment TS is tangent to the circle. Why don't you guys go ahead and try working these out here and see what you come up with. And when you're ready, hit play and come back and see how your work looks with mine. All right. And one of the things you need to pay attention to here, let's look at problem number 5. We have this right here is ST, and we have here RT. But what we're looking at specifically is the segment that the external segment of RT that's 8 units long. That is not the entire length of what we would consider the hypotenuse, because if this triangle is a right triangle, the right angle would exist right there, where TS would be tangent to the circle. Therefore, segment RT must be the hypotenuse of the right triangle if it is right. Therefore, it cannot be shorter than one of the legs. You must make sure you include the radius into your length for segment RT when you work it out. And in this case, when I plug the numbers 5, 12, and 13 into the Pythagorean theorem, those are numbers of a Pythagorean triple. So yes, that is a right triangle. And you'll do the same thing here. This internal piece of segment RT also is the radius, so it has to be 12 units long. So here I'm going to look at 12 squared, 16 squared, and 19 squared to see what we have here. And in this case, we wind up with an acute triangle. Therefore, segment ST cannot be tangent to the circle because we don't form a right angle. Now we're going to be looking at using, again, those tangent properties to find the lengths of segments on a circle or on segments of a circle. In this case, what we're going to be looking for is, can you identify what is the length of the radius of the circle? Now, I will, kind of give you a warning in advance. This unit is going to be one of the more algebra intense units that you've seen. We've seen some good algebra where we had to use trigonometry rules and special right triangles when we had all the stuff that we had to work with for radicals. Here we're going to be looking at a lot of really good algebra. Can you distribute properly? Can you factor properly? But it's not necessarily going to be just this lesson. I'm saying the entire unit will have a lot of algebra in it. So what they're telling us in the diagram, point B is a point of tangency. So I can claim AB is tangent to the circle. So we can use the Pythagorean theorem to show that triangle ABC is a right triangle and find R, which would be, in this case, the length of the short side of the right triangle. So we're going to start plugging our numbers here into the Pythagorean theorem. The hypotenuse is the sum of the radius and the external segment, 49. So that's why I say R plus 49 squared at this point. And of course, the other two legs would be R squared and 77 squared. Distribute here. Now, this is what I want to make sure that you're paying attention to. One of the things that I see students do a lot is they do not expand their expressions properly. This one here is the way that you need to do it. It's saying R plus 49 squared, so I have to say R plus 49 times R plus 49. I see a lot of students give me something that says R squared plus 49 squared, and that is terrible. Please don't ever do that. Your algebra teachers will cry. So will I. Now we're going to solve for R. At this point, we have R squared on both sides of the equal sign. But if I say minus R squared here and minus R squared here, you'll see that they both cancel out of the equation. So we can get 98R to equal 3528 when I simply subtract the 2401 from the 5929. And now I'm going to divide both sides by 98, and I would get the length of the radius in this case to be 36 units long. Now the next property that we're looking at here for tangent lines is that we have segments of circles, or we have tangent segments of circles that have a common point of intersection outside of the circle. And what we saw in our demonstration video, if you've gone and watched it, is that the segments that are tangent to the, or segments that share a point outside of the circle and are tangent to the same circle must be congruent to each other. So what we're seeing is that segment SR and segment ST, because they share segment S outside of the circle, but both segments are tangent to the same circle, then those segments themselves are congruent to each other, which will allow us again to recognize when I have things that are congruent to each other, how we can set up an algebraic expression or use algebraic expressions to solve equations. So in example 6, we see that segment Q is common between the two segments, and they're telling us in the instructions that QR and QS are both tangent to circle C. Therefore, those two segments must be equal in length. Setting the expressions equal to each other gives me 32 equals 3x plus 5. Solving for x gives me 9. And that's all they're asking us to do here. All right, ladies and gentlemen, go ahead and pause the video at this point and try working out these two answers, or working out these two problems. And when you have your answers, come on back and see how yours looks with mine. All right. So here on problem 7, what we're looking at is we're being told that point K is a point of tangency. Therefore, the triangle LKJ must be a right triangle. So we're going to use the Pythagorean theorem to figure out what the length of the radius is going to be. Plugging the values into the Pythagorean theorem, I'm going to get r squared plus 56 squared is equal to r plus 32 squared. Expand r plus 32 to say r plus 32 times r plus 32, and use your FOIL method, your box method, whatever your algebra teachers taught you, to distribute the entire expressions on the right side that say r plus 32 times r plus 32. Solving for r again, when I move one r squared from one side to the other, they wind up canceling out. So in this case, solving for r, I get 33. And the last one here, again, rs and rt are tangent to the same circle, so they are congruent to each other. Solving for, there we go. Solving for x, I'll actually get a positive 7 and a negative 7 when I take the square root of 49, but we're probably going to be more interested in the positive value than the negative value for a geometry application. So that's it for this lesson. We're talking about, again, introducing the vocabulary of segments that are used in circles, tangent, secant, chord, diameter, radius, those things. Make sure you understand the definitions of them. And this one specifically is focusing on properties of tangent lines, which are going to be perpendicular to the radius at the point of tangency. And if I have segments that are tangent to the same circle and intersect outside of the circle, they have to be congruent to each other. That's it for this lesson. If you have any questions, by all means, let me know what they are, and I'll be happy to work with you. But until next time, ladies and gentlemen, thanks for watching and take care.